the big picture of why we did systems of equations, why we did shaded region, why we did boundaries last night just ever so slightly, because it's all going to build into this one section. And I think I've mentioned this earlier, is that this one section will basically take us through all of next week. So this is the one section in this class that we spend a big chunk of time on. It's different, it's new, and there's a lot of parts to it. Today, all we're going to worry about is the beginning portion. Like I did on that last problem, how do we know where our region's going to be? Will we have a bounded region? Will we have an open top region, a bottom? It starts with the same principle of what we did yesterday, but taking it that next step, like the problem I just did, about figuring out where things ran into each other. And as we do that, we're going to create these, these constraints are basically what are given to you. The constraints are those inequalities that we were graphing yesterday. The constraints will be same idea that will be given to you in the textbook today. You'll just graph them. All right. So if I start with this one, yesterday we did a little bit of a shortcut. What's my shortcut with those first two constraints? Do you remember? It's only first quadrant. Very good. Now I know that it's going to be bound by the first quadrant, but look at my my third equation there, or inequality. What's going to be my x-intercept? It's going to be negative. So even though I know that the boundary has to be in the first quadrant, my third one tells me I should still draw quadrant 2 so I can get that intercept portion. Are we okay with that? It's just that little bit of getting used to visualizing what's going on. So let's see, we move this over a bit and try. So I know no matter what, I'm going to have to be first quadrant, but if I have a negative 15 for an x-intercept, I'm just going to say this is negative 15, comma 0. What's the y-intercept for that one? 5. Excellent. Let's say it's about here. 0, comma 5. Connect the dots. Continue on. Did it go through the origin? Nope. So it shades. Well, 0 plus 0 is 0, and 0 is smaller than 15. So we know that's moving down here, which means right away that this boundary is important to here, to here. So I know that it shouldn't be below this. Oops. I'm going to do that. I know that it shouldn't be below here at all because of the y is greater than or equal to 0. So I'm just going to label that at a 0, 0, because that's going to be what we call a point of inflection. Because, and you're looking at me crazy here, x is greater than 0, so it's going to be everything going to the right. Y is greater than or equal to 0, so it's everything above it. This graph shaded downward, but this stops it from going any further. Yes, ma'am. Yeah, this means just move it up and over. And then the next one, yes, sir. Inflection, where it changes direction. That's all it means. It's just a point of inflection is where it changes direction, and those are going to be those points where things change or where they intersect each other. Those are going to be the points that we're going to label. And then the last one here, we have x and y intercepts. What is it? 6 and 12. 6-ish will be 6, 12. Oh, sorry. 6, 0. And then say up here is at 0 and 12. What's 0 plus 0? I like this math, right? 0 plus 0. That's good stuff. I like that. Is 0 smaller than 12? Yeah, so it's moving inward. Which means I have to now figure out what this ordered pair is. I have to figure out what's the intersection between these two. So I solved that system of equations. Now, when we, even though that our problems, bless you, our problems here are all written up as inequalities, when I go to figure out what the ordered pairs are, where they run into each other, I'm going to treat them exactly like they were equations. I'm going to disregard the inequality for that because I'm trying to find the actual solution where they hit. Are you okay with that? Yeah. People tend to ask because they forget, what if I divide by negative? Don't worry about it. So, which one do you want to eliminate, the x or the y to start with? I would do the x. You know why? Look at their signs. They're alternating, right? See how one's positive, one's negative? You will be less likely to screw up when you add things together than you will be to subtract things. Because when you subtract things, a lot of times if you have negative values, you forget to change the opposite, things like that. So anytime you see opposite signs, eliminate that variable. It's kind of like the top tip, if you will. Use addition there. So I'm going to multiply that top equation by 2 and just rewrite it. I'm going to get negative 2x plus 6y is 30, which means I'm going to add those two together. 2 plus negative 2 is 1 plus 6, 7, 12, and 30. Y is 6. Substitute back in. 2x plus 6 is 12. Excellent. Everybody hear that? When you get to a lot of these, the numbers should be relatively clean. So when you substitute back in, if I just do 2x plus 6 is 12, x has to be 3. Subtract 6, divide by 2, you get 3. A lot of these you might be able to knock off real quick and off the top of your head. If not, you want to write it out? No big deal. It's fine. Which means now I have an ordered pair here at 3 and 6. So what are we going to do with these ordered pairs? Well, what happens with these types of problems is that they're going to ask you to maximize a function, maximize an objective function. I didn't show you what one looked like, but now that we have 4 ordered pairs, I'm going to give you something to maximize. That's what an objective function will look like. It just says C equals something. In this case, I just made it up 2x plus y. What this means is I'm going to take the 4 ordered pairs that I have. Put this on a clean sheet real quick. I'll double it up. I'm going to take my objective function, C equals 2x plus y, and I'm going to check it with my ordered pairs. 0, 0, 6, 0, 3, 6, and 0, and 5. I'm going to figure out which one of those ordered pairs gives me the maximum value. Which one of those ordered pairs gives me the minimum value. And all I'm doing is substitution. 2 times 0 plus 0 is 0. Like this math. 2 times 6 plus 0 is 12. Okay. 2 times 6. 2 times 3 plus 6 is 6 and 6 is 12. And 2 times 0 plus 5 is 5. Well, where's your minimum? 0, 0. This would be my minimum. Now, this is weird. This doesn't happen very often. It just happened to be dumb luck that Murphy made up something off the top of his head that wound up being equal. If that happens, not a big deal. It doesn't very often. But I would just say that these are maximums. Sir? You're looking for the boundary that you create. Here, we made this boundary where all these are moving inward, so all these ordered pairs would be in here. That's why we're looking for those ordered pairs, those points of inflection. That point of inflection tells you what ordered pairs to check. All right? So if you think about what we're doing, we're basically adding 2 steps to what you did last night. Last night you graphed a whole bunch of things. Today you're just figuring out where those things hit each other, and then you're just putting them into or substituting into some function that they give you. You don't have to come up with your own functions yet. That's next week. It's not bad. You just have to know how to read. Well, if we all bring glasses on Tuesday and Wednesday, we'll be fine. All right. Not terrible, is it? It takes a minute, but. All right, we'll go a real easy one. We'll do the next one with the full gamut here. This is kind of what the wording will look like in the text. Find the maximum and the minimum of the objective function. They give you the function. And then it says subject to the following constraints. And basically what you're doing is you're going to graph it all and figure out those points of inflection. Where do those lines intersect? 2 days ago, or yesterday when we graphed a few of these things, they had just less thans or greater thans. We knew that those technically had no boundary because you get infinitely closer and closer and closer. What we're doing today will always have greater than or equal to, less than or equal to, because it has to have some sort of boundary for some of these. It's not to say that you might not have a top to something. You could have no maximum, have a minimum. If you could have, if you think of a parabola, up like a cup. There's no maximum value to be, but there is a minimum value. Down like a frown. The maximum is at the vertex. There's no minimum because it continually opens. That's kind of what we're looking at here, but in terms of linear. What quadrant will this one be in, guys? Quadrant 1. Do I have to worry about any other parameters of that looking at that third inequality? No, because that was pretty quick. They're at 8s and 8s, so it's going to be easy. So if I throw this in quadrant 1, where are my intercepts for the third inequality? 8, 8, very good. So all I have to do is say this is 0, 8, and this one is 8, 0. Does this one graph towards 0 or away from 0? Towards 0. So that means it's moving inward here. So what do I have to label that ordered pair in the corner? 0, 0. Do I have the 3, in this case, I have 3 points of inflection. What are the 3 ordered pairs you got to check? 0, 0, 8, 0, and 0, 8. So you have your objective, 3 times 0 plus 4 times 0. 3 times 8 plus 4 times 0. 3 times 0 plus 4 times 8. Which one is the maximum? 32. You have a maximum occurs at 0, 8. The maximum value is 32. You have a minimum occurring at 0, 0 with a minimum value of 0. Yes, ma'am. The problems will come across where I'm going to ask you how many certain gift baskets should you have to maximize. Your answer would be you would sell 0 of the small gift baskets and 8 of the large gift baskets. That's kind of how how we're getting towards. Okay. Here, I'm just worried if we can figure out which one's bigger, then we'll understand what these numbers relate to. Okay, does that make sense? We're baby steps. All right, baby steps. It's a 3-day weekend. You're not going to do any of this stuff until late Monday night anyway. I get it. So I might as well at least try to start it out a little. All right, why fight it, right? I wouldn't. I'm not going to do it until late, buddy. I kind of keep it to you straight in case you guys didn't know. I keep it real, yo. All right. Maybe we'll do this one as our last one. Last one. And I'm going to do one that has a lot of horizontal verticals to it. We're running short. Since we're running short here, I'm just going to kind of plow through this a little bit. Yeah. What kind of line is x is greater or equal to 2? Vertical. Very good. What does it go through? 2. To what side do I have to graph this? To the left of it or to the right of it? Very good. You're welcome. All right. The next one is x is less than or equal to 5. What kind of line is it? Horizontal or vertical? What number does it go through? 5. Okay. So let's see. 2, 3, 4, 5. Do I graph to the right of this or to the left of this? To the left of this. Okay. Region. Region. What kind of line is y is greater than or equal to 0? Horizontal, and it goes through 0. Okay. So it's here. Which way are numbers larger than 0? Up. So now I'm here. With just those first 3, I've got 2 ordered pairs, don't I? Okay, I've got my 2 ordered pairs. I've got an ordered pair here at 2, 0, and 5, 0. So far, so good? Now, the next one is written in slope-intercept form. But wouldn't it be quicker just to move that negative 2x over and do a quick graph? This would be definitely a time that I would do that. Yeah, just bring it back over and use standard form. Because if you do that, it's just faster. So you have 2x plus y is less than or equal to 12. What's your x-intercept? 6. What's your y-intercept? 12. Now, excuse me, what's 0 plus 0? Is it smaller than 12? So this one put a lid on this. So if you think about the shape that we made, the trapezoid, isn't it? The trapezoid. I need to figure out the 2 ordered pairs here and here. I know the x-coordinates there, don't I? Because they're vertical. So one of them is 2 and the other one is excellent. 2, comma something, 5, comma something. Well, go back to the problem. What's 2 times 2? 4. 4 plus what is 12? It's okay. It's early. I'm figuring out where it hits. I'm using the ordered pair here too, because it hits here. 2 times 2 is 4. 4 plus 8 is 12. Okay. Direct substitution. Next vertical line, 5. What's 2 times 5? 10 plus what is 2? No, I said 10 plus what is 12? Do I have 4 ordered pairs now? Yeah. I got 4 ordered pairs. I've got 2, 0, 5, 0, 5, 2, and 2, 8. Does it matter which one you put in for substitute in first to find the maximum values? No. Let me. I know we ran way longer wanted to do it today, but we had too many questions come up, so let's do this. I think I have the PDF file on there. Let's just do 12, 13, and 14. It's on page 166. The PDF file it should be up. It's section 3.4, 12, 13, 14. There are 3 of them. They give you 3. Each one of them, or there's 3 inequalities, 4 and 4, and they give you constraints. They give you the objective function. You're finding max and min. They should be pretty decent. If you need flex, please sign out. It's not a big deal. These should be relatively quick and go from there. All right. And remember, you're doing basically everything we've done all week, all in one section. And as we get going in there, it gets a little nutty, but we'll be fine. Don't freak. Anybody have their computer up and make sure that PDF file is there? Make sure. I'll double check.